Good morning, ladies and gentlemen. We are going to begin our work energy review right now. Work is done when an applied force causes something to move, right? Just like,
Yep. If you pushing on it and it ain't moving, you ain't doing no work.
gotta move. A displacement. When the force is in the same direction as the displacement, it is this equation.
Just force times distance.
That's
But that's only when the force is in the same direction that the motion is.
Okay, let's take a look at units. Force times displacement. This is joules times a Newton meter. Joules, Newton meter.
Yeah, the units of force are newtons, the units of displacement are meters, and a Newton meter is a joule. It's a direct unit.
And if we break this down even more, a joule is equal to this. Now, this newtons is mass times acceleration,
Yep.
right? And the meter goes here.
Yep.
Okay, so these are our, if you were going to look at all the units all together, broken down into its simplest form, here it is. Work done by a constant force is also represented by this equation, work equals force times cosine theta delta x, where the angle, the theta is the angle between the force and the displacement.
Because not all the time is the force and the displacement in the same direction.
Yeah, do we want to, is that right here?
Now we'll get to that.
Okay. All right, so, and just a note on this, the cosine, if you know, what is the whole cosine of 180 thing? Cosine
Yeah,
of zero
yeah,
thing?
we'll get to that in a minute.
Okay. Okay, so work can be positive,
Oh, yeah.
negative.
Yeah,
or
yeah. In
zero.
fact, we're going to get to it right
Yeah.
now.
Work can be work can be positive, negative, zero, depending upon the relationship between the direction of the force and the displacement. So if the direction of the force and the displacement are in the same direction, that angle is zero, right?
Yeah, well, it's like if you're lifting something.
Yeah.
Let's see, you got something to lift. How about your water here? So if you're lifting it, what's the direction of the force? It's up. What's the direction of the displacement? Up. And so what's the angle between up and up? It's zero. And the cosine of 0 is 1.
Okay.
So if you're dropping, what's the direction of the force? It's got to be up.
Because otherwise it's going to drop.
And the displacement is down. So the angle between up and down is 180 degrees.
That's
And the
negative
cosine of 180 degrees is 0.
Negative 1.
Thank you. Negative 1. I was thinking about, and then if you're just carrying it across the room,
At the same.
the force is up and the displacement is horizontal. The angle is 90 degrees and the cosine of 90 degrees is 0.
Okay, so we don't do any work if the force and displacement are perpendicular to
That's
each other.
right. That's an important idea.
Okay. What if the given angle is not between the direction of the force and displacement?
It's like if you're pulling on the table in an up direction like this. Well, you do it.
You only had that angle right there.
That's right. And
Right.
we've got an example of this on the board
Okay, so
here.
Mr. Boykin was pulling on the table with imaginary rope, right?
Yeah.
And what if we gave you this angle? Well, what direction is the displacement?
Well, it has to be in the direction of the force in the direction of the displacement. And so if you're given that vertical angle, then you need the opposite side, which is the sine.
Yeah, so we want this one, which is really this one up here. And so that's gonna be force times the sine of theta.
Or you could solve for what the angle with the horizontal would be.
Yeah, you could try and figure out what
And
this
then that'd
is.
be cosine. But the idea is that a diagram is going to be crucial. Anytime you have one of these situations, a diagram will help you visualize what's going on and apply the ideas properly.
Okay, power is the rate at which work is done.
Yeah.
Work over time. And our units of power are joules per second, or a watt.
What?
Okay, what? And if we break down our units here, so watts or power is a joule per second. A joule is a Newton meter, and we just went over how this is mass times acceleration, and that's a meter. Put all over seconds, and this is what we have.
Yeah, this is where things come from.
Okay, and if we use our symbols here, we've got power is work over time. Work is force times displacement, and D over T is velocity. So I don't think we really mess with this one too much, but you can see.
You
how
never
we get
can
to it.
tell.
Yeah. Okay, work changes energy. Yes, it does. Work energy theorem. Work equals force times distance, which equals the change in energy of a system.
This is one of the foundational ideas in physics.
Yes. Ooh, what was that? That was cool. Okay, mechanical energy is the form of energy due to the position, potential, or movement of a mass, kinetic.
Yep.
And gravity can do work. Yes, it can. So work equals force times displacement. In this case, it's the force of gravity. We have an equation for the force of gravity. It's m times.
Yeah. So if you're doing work against gravity, even though the force of gravity is down, if you're lifting something, the force that you're applying against gravity is up. So that's even though the acceleration due to gravity is negative, it's down. If you're pushing up against gravity, your force is in the up direction, so that would be positive.
Yeah, doing work against it. Gravitational potential energy, UG, energy due to elevation above a reference point. And so work, here's our equation for UG. Why is it so little? We've got mgh,
Yeah,
right?
that should be capital. Huh?
And this is just force times displacement written in another way.
It's a real
basically.
simple thing. Work equals change in energy.
Okay, and here we go. Practice problem. Mr. Boykin does 188 joules of work. So work equals 188 joules. Carrying a 7.5 kilogram bowling ball. Of course, it's carrying a bowling ball. 7.5 kilogram bowling ball up a ladder. Okay.
How
so,
high above the ground?
So he goes from here. Let's make UG 0 here, obviously.
Well, that's a very important thing. You can make potential energy into zero wherever you want it to be. It's there. It's not a absolute idea.
Yeah, and then UG up here is going to be 188 joules, right?
Yeah.
Okay. So how high above the ground did he carry it? Okay. Let's see. So we know that UG is equal to mgh here.
Yeah.
Okay, because we know that work changes energy. Okay, and we're solving for this, so we're just going to divide by mg. Okay, so that equals the height. I think we can do this. So let's just go ahead and plug UG in, which is 188 joules, right?
Uh-huh.
And then mass times g, I'm just going to call this 75 newtons right there.
7.5. Oh yeah, 75 newtons.
Yeah, but multiply it by 10.
Yeah, sorry.
Okay, it's all good. Okay, so 188 divided by 75, and we get 2.5.
2.5.
Okay, so 2.5.
2.5 meters,
Yes.
which is about up where the lights are. No. It's about halfway up the ladder.
1, 2. Oh yeah, right there. Okay. All right. So how high did you carry it? 2.5 meters. Okay. And then we have our kinetic energy varies with mass and velocity. So we also have that the kinetic energy is 1/2 mv squared. And we know that work changes the kinetic energy.
Yep.
Okay. The law of conservation of energy. Energy can either be created or destroyed, only changed from one form to another.
Big idea here.
Okay, so to simplify, we will consider only mechanical energy. Now, if you remember, yesterday, I think it was, we had like the law of conservation of angular, I can't remember what we were talking about.
Well, we also had mechanical energy, including energy stored in a spring.
And rotational, right?
And rotational kinetic energy.
Yeah, so this is kind of bringing it back even further, simplified even more, and we're just looking at kinetic and UG.
Yeah.
Okay. Conservation of mechanical energy. Here is our equation. For a closed, isolated system, the total mechanical energy is constant.
And this is your starting point. You should always
Always.
start with this simple thing and then look at what kind of energy is present.
Yeah, and I mean, you could even have started with this just to do this equation.
That's
you
true.
could have, yeah. Okay. All right. So energy initial equals energy final. So here are our conservative forces. So gravity, springs, and electrical forces. And our non-conservative forces are friction and air resistance.
Now, what the deuce does this mean? Well, a non-conservative force, friction and air resistance, take energy out of the system because friction converts whatever kind of energy, kinetic energy, into heat. Air resistance does a similar sort of thing. So the law of conservation. That's why you'll frequently, whenever you see in a friction on something is sliding on a frictionless surface, they're talking about no friction, so it's a conservation issue.
And if you remember, off our springs, right, that was part of that energy total,
Yeah.
you know, conservation of energy. And then we were talking about the ups equal the downs here for this, right?
Electrical forces?
Yeah, and this idea of a conservation of charge at some point, I believe.
Well, yeah, but you also, that's Coulomb's law. If you
Yes.
if you have electrical forces or magnetic forces, they obey the law of conservation. They don't take energy out of the system.
Yeah. So that's kind of, if you remember what we're talking about those things, which you should, then that's how those apply there, okay? Okay, so Mr. Boykin said you should always start with this, which is absolutely true. So we know that we have kinetic plus UG in the beginning. Go. This just means the beginning. Kinetic plus UG in the beginning equals the kinetic plus the UG at the end. And we can break this down even more from there into 1/2 mv squared mgh.
And see, the thing is, this makes a pyramid. And why you always want to do the pyramid is almost every time there's going to be something that's zero. And the bottom line looks complicated and confusing. If you can make something zero and get that out, it simplifies things.
Okay, so oh, great question here. So on the test, how are you going to recognize the difference between a work problem, an energy problem, and an impulse momentum type problem?
Yep.
And they look very similar. And the big difference here is that with work, we are talking about distance. With impulse, we've got time in
Yep.
there.
Yep.
Okay. And that's the biggest difference there. Now, we're gonna go back through and add for the AP test. We went through and
That practice test, don't tell them don't
well-
tell them the answers.
oh well, that's at the bottom of the thing, anyways.
Oh, yeah, okay, yeah.
But we went through and labeled the answers for what questions go with what review section for you guys.
Yeah.
So for this one, it's 8, 10, and 12. Go ahead and get some practice in.
Sweet.